All right, thank you very much for having me here today. We are going to continue with chapter 9. Before this, we were talking about hydrocarbons. We said hydrocarbon consists of carbon and hydrogen, and we look at saturated hydrocarbon in the form of alkane. So if you look at saturated hydrocarbons, they only consist of single bonds. So today we're looking at other hydrocarbons, and in this case we're looking at those that contain double bonds, and next few lessons we look at those that contain triple bonds as well. So if you look at this diagram here, and we talk about unsaturated hydrocarbons, you say unsaturated hydrocarbons are carbon compounds with hydrogen in which there are double or even triple bonds between the carbon atoms. So now we are talking about carbon atoms itself. There's something what we call double bonds between the carbon atoms or triple bond between the carbon atoms. Just bear in mind, if it's a double bond between the carbon atoms, you have two valence electrons that have been shared. If it's triple bond, it will be three valence electrons that have been shared between the carbon atoms. You see, a double bond is formed when two pairs of electrons are shared, and triple bond is formed when three pairs of electrons are shared. So something for you to think about. Today we are looking at the double bond, and there's a name for it. If that particular hydrocarbon molecule has the double bond, most likely it is of an alkene structure, alkene, so it ends with E and E, not A and E. So make sure you know the difference between alkane and alkene. So if it's a double bond, it is an example of what we call an alkene structure, and that is different from an alkane structure. So move on to the next slide. Alright, so now we are talking about alkene here. It is that alkenes are homologous series of hydrocarbons with at least one carbon-carbon double bond. The general formula for the alkenes with a double bond is CnH2n. So when we were talking about the general formula of alkene, it is of CnH2n plus 2. If it's alkene, it is of CnH2n. So make sure you know the difference between alkane and alkene. So essentially the presence of carbon-carbon double bond means the alkene are described as unsaturated molecules. It says that alkenes are more reactive than alkanes, which do not have any carbon-carbon double bonds. So when we are talking about alkene, once again, the general formula that we use is CnH2n. Is a particular homologous series, very different from what we have for alkane. Because in alkane, its formula that it uses is CnH2n plus 2. If it's alkene, the general formula is CnH2n. And when we talk about alkene structure, it consists of double bond instead of single bond. So make sure you know the difference between alkanes and alkenes. Move on to the next slide. Alright, here, so it's talking about alkene once again. So the simplest alkene is ethene. Why is it not methene? Methene do not exist because CH4, it exists as an alkene, but it cannot form any double bonds. It cannot form any double bonds with another carbon because it only have one carbon. So if it's an alkene structure, let's say we are talking about ethene, it consists of two carbons, it has four hydrogen, it do not have six hydrogen, it only have four hydrogens here because it has that one double bond. So it says the next member of the series is propene, which is C3H6, which has an additional CH2 unit. It says the angle of the bond angle around a carbon atom with a double bond is 120 degrees. So you can see the structure is actually different from what we have for alkane. If we look at ethane previously, we know that structure is of the tetrahedral shape, and we know the bond angle is approximately 109.5. That's something that we have discussed when we are talking about the alkane structure. When you're talking about alkene structure, let's say you look at ethene, propene, butene, and we know ethene has two carbon, propene has three carbon, butene has four carbon. We know that all of them has one double bond, and the bond angle, you can really see the bond angle is actually 120 degree. The bond angles around the carbon atom is actually 120 degree, not 109.5, because in this case it's not of a tetrahedral shape. It's of what we call a planar or flat shape. So something for you to consider. So this particular shape is actually of planar. So PLANAR. We talked about trigonal planar previously. We are talking about some of the shape, like boron trichloride, for example, is of a trigonal planar shape. So in this case, it's of planar, very similar to that trigonal planar shape, and you can also call it the flat shape. So if we are talking about these structures here, you can see that ethene, propene, and butene. What you can observe here, you can see that all of them are still non-polar because they are symmetrical. They are non-polar. If you come across a hydrocarbon, it is of non-polar if it consists of that carbon and hydrogen. So in this case, ethene, propane, and butane consists of carbon and hydrogen, and is symmetrical, or the structure looks symmetrical. It is non-polar, which means there is only in intermolecular forces. So intermolecular forces is the forces between one molecule and another. Most likely it has to be a dispersion force. So you can see dispersion force increases is the molecular size increases. So in this case, that if you have ethene, propane, and butane, you can say that the molecular size increases, the molecular weight increases, which means the boiling point in this case also increase. So ethene has a boiling point of minus 78.4 degrees Celsius, propane has a boiling point of minus 47.7 degrees Celsius, butane at boiling point of minus 6.3 degrees Celsius. You can see the boiling point actually increases. So for ethene, the uses will be a wide range of chemicals. For propane will be manufacture of propane oxide and polymers. For butane will be manufacture of butanol and polymers. We'll look at these different examples here and their uses or their reactions as well. That is something that we're going to concentrate for today. Moving on to the next slide. Alright, so writing formulas of alkane. If you still remember, the last time we stopped at somewhere when we talk about covalent molecules, we look at structural formulas. Structural formulas is very similar to the valence structure as previously discussed, and we know the imbalance structure it shows the lone pair electron. In this case, the structural formula, they do not show the lone pair electrons, so in this case they only show the bonding electrons but not the lone pair electrons. So you have something called the electron dot diagram. Electron dot diagram is also known as a Lewis structure. You can see that it has a dot and crosses. And you have something called the condensed structural formula. Condensed structural formula is also known as the semi-structural formula. The difference between condensed structural formula and structural formula is that condensed structural formula do not show the bond. So in this case, let's say we look at ethane, for example. Ethene has a formula. It follows the formula CnH2n, and we know that ethene has 2 carbon and 4 hydrogen. Can you see it here? The condensed structure formula of ethene is CH2CH2, whereas the structure formula will be C2H4, but in this case you show the bond, and you can see there's actually a double bond between the carbon. Can we see that? If you look at propane, very similar trend. This contains 3 carbons. So the electron dot diagrams, or it's also known as the Lewis structure, it shows the dots and crosses, which is the bonds between that particular or the electrons that have been shared between those atoms within the molecule. If it's a condensed structure formula, in this case the propane has a condensed structure formula of CH2CH3. You can see there's a double bond between the 2 carbon, which means that 2 valence electrons are being shared by each of the carbon atom if it's in the double bond, as you can see. So make sure you know the difference between alkane and alkene. If you are talking about alkane, the formula will be CnH2n plus 2, alkene will be CnH2n, and each of these is a homologous series, which means that alkene has a different homologous series as compared to alkane, and so on. So its properties will be different. From some of its properties will be different, and that's something we are going to discuss for today. Moving on to the next slide. Alright, so we're going to continue on the structural isomers. Structural isomers, based on what we discussed on alkane, we see that structural isomers are molecules that have the same molecular formula but different structural arrangement. So if you look at this diagram here, you can see that you have structural isomers of butane. We have but1N, we have but2N, and we have methylpropane. So all of them has the same molecular formula, which is 4 carbon and 8 hydrogen. Can we see that? 4 carbon and 8 hydrogen. If you were to compare to alkane, we know that alkane has a formula which is CnH2n plus 2. In that particular case, in alkane, it will be 4 carbon and 10 hydrogen. So in this case, it will be 4 carbon and 8 hydrogen. 4 carbon and 8 hydrogen. So you can see that but1N has a double bond on that particular first carbon. It may appear like it is on the second carbon, but it's actually on the first carbon. So in this case, you do need to name it as but1N. You cannot just write butane, because when you talk about butane, which is what we have been referring to of an example of an alkane, it does not have any double bond, but in this case but1N has 1 double bond on the first carbon. But2N has a double bond on the second carbon, as you can see here, and then the third one, or the third structure, as you can see, is methylpropane. So methylpropane consists of that propane structure that has a double bond. At the same time, it has the methyl, which is the side chain. If I'm going to draw this, you can see that there's a side chain. You can actually, this is referring to a side chain, or even the one at the top is referring to a side chain as well. So it's known as a methylpropane. So it says here, when naming alkene isomers, the carbons are numbered from the end of the carbon chain that gives the lowest number to the first carbon in the double bond. The location of the double bond in the molecule is indicated by this number. So you can see the double bond in boot 1N is between carbons 1 and 2, and double bond between boot 2N is between carbons 2 and 3. So if the double bond is between carbon 1 and 2, your name in this case, because it has 4 carbon in the main chain, is known as boot 1N. If it's double bond in between the second and third carbon, that particular structure is known as boot 2N. So these are what we call structural isomers. So bear in mind, when we talk about alkane previously, we know that alkanes have structural isomers. If the number of carbon is more than 4, that's something that we have discussed. In alkane, it also have structural isomer. As long as the molecular arrangement is different, even though molecular formula is the same, but the structural arrangement is different, that particular alkane will have what we call structural isomer. Moving on to the next slide. Alright, so reaction of alkane. If you still recall, when we talk about alkane, we know that alkane reacts with oxygen to produce carbon dioxide and water. So when we talk about alkane, it also reacts with oxygen to produce carbon dioxide and water. But something you need to bear in mind. Alkane has lesser number of hydrogen, so it actually produces less water molecule. It also requires less oxygen as well for its combustion as a result. And that is a general idea that you will see or you will find between an alkane and an alkene structure. But both of them can undergo complete combustion. Complete combustion means that it releases carbon dioxide and water only. It will not release any other product. In this case, it has complete combustion because it releases carbon dioxide and water, and the state of the reactant products is in gaseous form, as you can see. So make sure you know that alkene, they can undergo complete combustion, which means they can burn under presence of oxygen to produce carbon dioxide and water. Moving on to the next slide. Alright, continue here. It says that alkanes are able to take part in addition reactions. You see, in addition reactions, part of a reactant becomes bonded to one carbon in the double bond, and the other part of the reactant becomes bonded to the other carbon atom in the double bond. The double bond is broken and a single carbon-carbon bond is formed. So what does this mean? Let's just look at the next slide for me to explain these addition reactions. So as you're probably aware, when we're talking about alkane cannot really undergo addition reaction. It can undergo what we call substitution reaction, which is something we're going to discuss later on as well. But in alkane, it cannot undergo addition reaction because it is a saturated hydrocarbon. No other atoms or no more new atoms can be added to that particular compound. But if we are talking about an alkene structure, as you can see here, let's just say this structure is of ethene because the formula is Ce2H4. Ce2H4, we can see that it can undergo the addition reaction. It can react with bromine gas. It can react with water molecule in the form of H2O. It can react with hydrochloric acid. It can also react with one another to form what we call polyethane. But if you look at bromine gas, which is the first reaction that you can see in this particular diagram, bromine gas in general is orange in color. So what this is trying to say is that if ethene reacts with bromine gas, eventually the bromine gas will become colorless, because bromine gas will no longer exist because it will be part of that particular compound. So the point here is that bromine gas can be used to test for unsaturation of organic compound. If that particular organic compound is unsaturated, the color of bromine gas will change from orange to colors, and we know that the particular structure that you have or the unknown compound that you have is an unsaturated compound, and it's not of a saturated compound. That's something that you can use as a test. If you add water molecules to that particular ethene structure, it will become ethanol. It's an ethanol solvent in a cleaning agent. If it's hydrochloric acid being added to the ethene structure, you get chloroethane. It's once you add refrigerant and aerosol spray propellant. If they are adding one another, if the ethene structure is adding one another, you get what we call polyethane. They are used in plastic. So something for you to consider once again, because alkanes are unsaturated hydrocarbons, means that more atoms can still be added. Bear in mind, if it's unsaturated, means that more atoms can be added because it contains that particular double bond. Means the double bond cannot be broken to form single bonds as a result. So something for you to think about when we are talking or discussing the addition reactions of ethene. Moving on to the next slide. So now technically we are on the final slide here, so we are almost there. There's something called benzene ring. You may come across or you may have heard of it. So it's a Michael Faraday isolated a new hydrocarbons known as benzene, which is in the formula of C6H6. And then you have someone called August Calulet then proposed a ring structure in which alternate carbon atoms were joined by double bonds in 1965. So you see, it is now known that benzene has the
ring structure, but it's not have alternating double and single bond. So initially, that particular structure, as being described by August Kaluli, looks something like this. So if you look at this diagram here at the bottom, so the one that I'm circling in red, which is what is being proposed by August Kaluli, that the double bond and the single bond were actually alternate. But it turns out not to be true. And what you get something like a bold structure. If you look at this structure here, and I'm going to circle this in blue. So this is how it looks like, and this is what we call a benzene ring. And even the green structure in the middle, and we're going to highlight this I'll circle this in purple, is also acceptable. You can see that its molecular formula is C6H6. It contains 6 carbon and 6 hydrogen. And in between it has that double bond. And what they were trying to say is that the electrons within the single double bonds will actually delocalize. So the electrons will be moving around that particular benzene structure, even though the double and single bonds do not move, but the electrons will actually move around the structure, and the length of the bond, the single double bond, is actually the same. And in a way, it is also more stable. And what scientists have found is they found that this benzene ring is more stable than other unsaturated compounds that we have sort of discovered or we have sort of used. So in this case, benzene ring is something interesting because it's also the ring structure, but it consists of single and double bonds. Anyway, it's unsaturated, and that means that, and I'm giving you a hint here, it can undergo some reactions. To a certain extent, it is reactive. But if you're comparing to some of the other unsaturated compounds, it is not as unstable as some of these unsaturated compounds. So once again, benzene has a more formula of C6H6, and it has a particular ring structure, so usually it's known as the benzene ring, which looks like a ball, like a shell of the ball. As you can see, as you can see in that particular diagram that I'm circled in blue. Alright, so we are done here. What I need to do is that I need to complete the questions for part 1 of chapter 9.2, which is on unsaturated hydrocarbons. And the next few lessons I will be guiding you through on the triple bonds, or hydrocarbons consist of triple bonds, along with the naming of these particular unsaturated hydrocarbons. If you have any question, we are very welcome to email me or post it out on social stream, and I'll answer your question then. So I'll see you back in class in our discussion session. See you then.